Okay, so now it's time to study the lecture note number 4. So we switch to electronic pen. Okay, just 1 second, please. Oops. Okay, right. So today we're gonna study some details in section 2.3 in chapter 2. The main keywords is bandgap energy and density of states, or simply shortly speaking, DOS. And now it's time to study the physical meaning of doping in crystalline silicon material. So as we have learned, the very first question that we had uh, in the week number 1, I have asked you what the semiconductor is. In terms of resistivity or conductivity, you may answer that the resistivity of silicon material or semiconductors lies in between the resistivity of conducting materials and conductivity of insulating materials. So even we have learned a quantitative value of resistivity for silicon material, which was 10 to the minus 3 ohm centimeter to 10 to the plus 3 ohm centimeter. In this lecture note, since we have learned the concept of bandgap energy, even in case of silicon material, the bandgap energy was 1.12 electron volt. So now we are ready to classify the materials into 3 different categories again, into uh, semiconductors, conductors, and insulators. On the left-hand side, you can see the energy band diagram for crystalline silicon material. The valence band is nearly filled with many electrons, and those electrons coming from the uh, electrons which has participated in making the covalent bonds in between 2 neighboring silicon atoms. And at room temperature, a few electrons, not a few, actually 10 to the 10 per cubic centimeter, right? And it was denoted as N sub I, right? The electron concentration of intrinsic silicon semiconductor material. So per given unit volume, 1 cubic centimeter, 10 to the 10 free electrons or conduction electrons here and there can be found. So in that sense, the conduction band is almost empty. Only 10 to the 10 per cubic centimeter free electrons can be found. Okay, what about the silicon dioxide, which is the widely used insulating material in CMOS device or MOSFET, or simply speaking, transistors in CPU, NAND, and DRAM. So this silicon dioxide is an insulation material. So in terms of bandgap energy, the bandgap energy of silicon dioxide is 9 electron volt, which is almost 9x higher than the bandgap energy of silicon material. So the physical meaning of very high value of bandgap energy indicates it is very tough or hard to create the electron hole pair or EHP. To create a single number of EHP in a certain material, in this case a silicon dioxide, the minimum required energy to generate EHP or to create free electron and free hole, minimum required energy for that is a bandgap energy, in this case 9 electron volt, which is almost 9 times higher than the bandgap energy of silicon. So for given thermal energy, or once silicon sample material and silicon dioxide material has been exposed to the same temperature, say 300 Kelvin or room temperature, for given and limited thermal energy to create uh, a bunch of electron hole pairs. Which material can generate more number of electron hole pairs? Well, since silicon material has almost 9 times a smaller band gap energy compared against the silicon dioxide, therefore we can make the conclusion that, well, definitely silicon should have a humongous number of electron hole pairs compared against the number of electron hole pairs in silicon dioxide, because silicon dioxide has high band gap energy, even almost 9 times higher band gap energy. In other words, to have an identical number of electron hole pairs in silicon dioxide versus silicon, maybe almost 9 times higher energy is required for silicon dioxide. Okay, what about the matter? Well, a certain material is a metallic. We can say that part of the conduction band has already been filled with many free or conduction electrons, so it's ready to flow current. So herein, part of the conduction band from here to here, this indicates conduction band. This is a top edge energy level of conduction band. This is the lowest energy state in conduction band. So part of the conduction band has already been filled with the free electrons, so it's ready to flow current. Well, going back to the silicon and silicon dioxide energy band diagram, can you see that conduction band here and there? There, conduction band is almost empty. It is not uh, partly filled with many electrons. It is almost empty. What about the silicon dioxide? Definitely, it is almost empty. What about the metal? Part of the, maybe according to this figure, maybe half of the conduction band has been filled with many free electrons. So intrinsically, metallic material has many number of free electrons in its conduction band. Okay, so some device physicist has claimed that all metallic material doesn't have any band gap energy. In other words, no band gap. Then, in other words, the part of the conduction band can be filled with many electrons. Okay, so in summary, insulators have very large band gap energy. For example, silicon dioxide, its band gap energy is 9 electron volt. What about the semiconductors? Semiconductors has a relatively smaller band gap energy. For example, the silicon, its band gap energy is 1.12 electron volt. So I would like to ask you to remember these two numbers. The band gap energy of silicon dioxide is 9 electron volt, and band gap energy of silicon is 1.12 electron volt, would be the common knowledge in the field of device community, electronic device community, especially the silicon-based transistors to be used for DRAM access transistors, and then the B-cell transistors, and basic components in cache memory or static random access memory as well, and even the logic transistors for CPU, ZPU in digital circuitry. All right. And here metals, as I told you, no band gap. Okay. In other words, its conduction band has been already partially filled with many electrons. Okay. And the next slide is going to talk about some how to measure the band gap energy. Well, as I told you, the band gap energy of silicon is 1.12, and SiO2 is a 9 electron volt. So, uh, so you may have a raise up this kind of question: how to measure the band gap energy of all the materials. Um, one of the experimental ways to measure band gap energy for a given material is as follows. Here, as described here, the band gap energy E sub G can be determined from the minimum energy of photons. So photon is a light. So light consists of many solid like a rigid or some balls uh, having its own energy. And that is named as a photon. And this photon's energy is described and very dependent of its own wavelength or frequency. So energy of photon is ha times, not h, ha times mu. And mu is a frequency, so ha times 1 over lambda. Well, you don't need to worry about how come the 1.26 comes from. Just remember the longer the wavelength is, the smaller its energy is, and the higher its frequency is, the higher its energy is. Okay? So photon's energy can be modified with its own frequency or wavelength. So we engineers has developed a very special measurement equipment. Uh, Here is a dial, and by rotating it clockwise and counterclockwise, you may modify the frequency of the light to be output from this special equipment. So this light has a bunch of photon, and depending on the wavelength or frequency or mu, as I used, uh, the photon's energy can be determined. So this special equipment tool is named as a monochrometer. So this monochrometer can create uh, many photons, but all the photons have this identical frequency or wavelengths. Again, monochrometer can create many photons which have identical uh, frequency or wavelengths. So for given photons, a certain material has observed those photons. Then this energy, Ha times mu, photon's energy can be delivered to the sample material, and the sample material may or may not observe the photon energy. So how come the sample material can observe the photon energy? It's very dependent of the band gap energy. If the photon's energy, Ha times mu, is smaller than band gap energy, say that this electron, which has participated in covalent bonding in between two silicon atoms, say this guy. So this guy has received the photon's energy, but this photon's energy is smaller than the band gap energy of silicon, say 1.12 electron volt, and observed energy is say zero point 0.6 electron volt. Then can you claim that this electron which has participated in this covalent bonding can be becomes loose and broken this covalent bond? Yes or no? As I told you, the minimum required energy to create the EHP is band gap energy. If a certain given energy is smaller than band gap energy, it is hard to break the covalent bonds. So now the situation is as follows. R mu that you have delivered is smaller than band gap energy. So these covalent bonds cannot become broken. In other words, this electron cannot be excited up to the conduction band. This process cannot be happened because of what? Because you didn't deliver sufficient amount of energy to this sample material. So using this concept, you can smoothly and very minutely adjust the wavelength or frequency of the photons. Okay, then at some point, at a certain frequency or at a certain wavelength, this sample would have a bunch of free electrons. Otherwise, not too many free electrons in its conductor band. So using this concept, what if you apply a plus and minus voltage difference in between two regions? And if there are many electrons created in conduction band, these electrons would move toward the plus anode electrode. Therefore, those newly created electrons would make a current flow. So for a certain, at a critical frequency or wavelength, if the silicon sample can flow current roughly, then we can say that this frequency or this wavelength is quite well matched to the band gap energy of the sample material, in this case, the silicon. Okay? Now, since you know the band gap energy of silicon 1.12, you can plug in here 1.12 and using a Ha, which is the quantum constant, then you may calculate the wavelengths of the photon, which can be used to create a bunch of free electrons and conduction electrons. So using this concept, we can measure directly the band gap energy of all type of materials, as germanium. It turned out that this band gap energy is 0.67, which is almost half of the band gap energy of silicon. And what about this guy, 35 compound semiconductor, right? It has zinc blend material structures. So these guys, band gap energy is 1.42, is a slightly wider band gap energy than the silicon band gap energy. So I'd like to ask you to remember those three band gap energy values for germanium, silicon, gallium arsenide for your knowledge. And maybe if you're interested in having a job in the field of semiconductor process and devices, you should remember those three numbers for your reference. Okay, now let's switch the gear to understand density of states, or DOS. So whenever I'm talking about and teaching this density of states, you may always think about how the states are arranged and placed in a plane. When you take a plane, if you reserve the business class, you know, you have a more room for your legs. But if you take a purchase economic class ticket, and a very small amount of rooms are available for your legs because all the uh, seats, economy seats, are packed in a limited area. Those things can be found in conduction band and valence band. Density of state means, when I'm teaching you how newly created energy states are created, I simply mention that there is many new energy states, and they are almost looks like a continuously created. However, in quantum, following the quantum physics, the energy states is still discrete. However, the state-to-state energy difference is very tiny and small, so we can say that it's almost continuous. However, in real, the energy state to the other energy state, the energy difference in between two energy states are very discrete and very tiny. Okay, so here the energy, two different energy state has been split with delta E energy values. Okay. Here the question is then how those newly created energy states are distributed out within a conduction band. Are those energy states equally distributed in conduction band, or are they unequally distributed in conduction band? Well, the answer is the energy states are newly created. That's true, but the state-to-state energy difference is quite different depending on the energy levels. So at high energy level, the energy states, state-to-state energy difference is delta E is very small. However, relatively lower energy levels, the state-to-state energy difference, delta E, is quite high. Okay? So for given volume and for given energy value, so usually we are using an electron volt in the unit of energy. So for per unit energy and per unit volume, how many energy states are available? So DOS has in the unit of number of energy state per energy per volume. So for given volume and for a unit energy, how many energy states are created and available in silicon material? So people, device physics that has run and conducted many previous studies, and it turned out that the delta E or the state-to-state energy difference is getting smaller and smaller and finer when the energy level becomes higher and higher. So on the right hand side, you can see that x-axis indicates density of state. So it was described as G sub C of E. So as a function of energy in conduction band, uh, this function of G indicates how many energy states are there. So as described here, uh, at this energy level, the number of states per unit energy and per cubic unit volume that is described here. Okay, interestingly, as energy increases, the number of energy states increases, but monotonically decreasing. I would say not monotonically increasing instead of saying monotonically decreasing. Anyhow, the number of energy states is keep increasing. Okay, and this uh, density of state is quite well matched to the uh, how the states are arranged and placed in a plane. Okay, all right. And on the right hand, on the bottom side, you don't need to derive the equation for density of states, but we can use it later. And one thing that you should take a look at is density of states in conduction band is proportional to the square root of energy minus E sub C. Okay, and valence band is quite well, symmetrical. I mean, the density of states in valence band is quite well symmetry of the density of states in conduction band, other than the different mass of holes versus mass of electrons. So as described in this equation, Mn asterisk, here Mp asterisk. So this M sub n means electrons mass, but here asterisk indicates effective mass. So effective electron, effective mass of electron. Okay, and M sub p asterisk indicates effective hole, effective mass of hole. Okay, so M sub n asterisk, M sub p asterisk, those two key concepts will be studied later on. So in this case, just try to uh, understand it as a kind of mass of electron or hole. You know, the key concept in this lecture note that I would like to teach you is density of state is proportional to the square root of uh, energy. Okay, so at a very high energy level in conduction band, the density of state is quite high. How about in valence band? Near the top edge of the valence band, the density of states is quite low. So not too many energy states are available compared against here a very low energy regime. There are many energy states are available. Okay, right. So before learning the doping, let me stop here and please have a short break time. And in the next movie clip, I'm going to teach you the basic concept and fundamentals of doping technique. So how comes the doping can modify and modulate the total number of free electrons in silicon material. As I told you, one of the ways to tweak and modulate the total number of electrons in silicon material was doping, right? So the Simple concept of doping is to replace the silicon atom with a new atom, which comes from column 3 or column 5 in periodic table. So we will see some details in the next upcoming movie. Okay, please have a short break.